Okay. System dynamics. In this lesson, we will continue with the response parameters. And stability. Okay? We will define it and solve it in terms of the what? In terms of the differential equations. Okay? So, just remember that the general differential equation are x dot plus ax is equals to the b, and x dot dot plus ax dot plus b is equals to the c. What's the definition of these things? Which order? First order, right? In the second case, it's the second order. Okay? So, what's the solution of these terms? Just remember the previous lesson. We solve this in terms of the what? The xt, in terms of the a and b, right? And so, b divided by a plus x0 minus b divided by a e over minus a t. So, what is this? What's the special name for this thing? Steady state, right? What is this thing? Transient. For the first order equation. And so, what about the solution of these terms? We should not drive the whole equation exactly in here, but I can guess that the xt is equals to what? The c1 times e over r1, this is the root 1 t, plus c2 e over r2 t plus c divided by b, right? And so, what is this term? This is the steady state, right? What is this? This is the transient, right? And so, why this is transient? What's your name? No, not you. Behind you. Yağmur. Yağmur. Why we call it the transient response?
Because it's not stable, can
Change with, it's dependent on the what? Time, right? And so this exponential term, if the r1 is negative and then it goes to what? To the 0, right? When the t going to the what? Infinity, right? And so this is why we can say that this is the transient. So just like the what? Just like the first one, okay? And so if we solve this equation, the c1, c2 is a constant value, right? And so how can we solve this equation? Based on the what? Yes, initial value. And so, how many initial values should be used to solve this equation? 2. And so, which are, just say it, and the derivative, x0 and x dot 0, right? And so, it's directly representation of what? The time behavior on the what? On the time response. And so, this R1 and R2 derived from the what? The Laplace notation or the solution of this integral. And so, this R1 maybe is equal to the what? A minus plus minus a square minus 4b divided by 2, right? And so, this is our root notation, the minus and positive values are given at this condition. Okay, and so this is directly related to what the stability values, okay, or the stability. What's the meaning of the stability? Can anyone guess that? Stability means that if if the time going to the infinity, and so the R signal either closing to 0 or the infinity value. If we are closing to infinity, and so our system is unstable. Otherwise, if we are going to what the 0, and then we can say that this system is the stable. Okay? But we need to check this value based on the what? Based on the our transfer function approach or the Laplace domain approach with the basis of the, what? The root of this equation. Okay? This is important. But before that, we need to define the 252, the time constant. Okay? So, consider this system like x dot plus ax is equals to the what? Is equals to the b. Okay? And so, how we can define the time constant? Just remember the previous lesson, guys. What is the definition of the time constant? So, in order to remove the forced response, we need to remove the what? The b value in here, because the b is our input. If we equalize the b is equals to the what? The 0, and then our equation turns into the what? The x dot is equals to the a times x, right? This is our equation. And so our solution is equals to what? The x0 times e minus at. Okay? And so, how our system behave under this equation? So, we can draw this t and xt value, and so for example the x0 can be assigned in here. Okay, and so how should I draw this equation? Go to 0, and so just like this one, if the what? If the a is greater than 0, right? And so what happens if I increase the values of the a here? Huh? Decrease? Yes. And so, for example, this dot line is the what? The 2a value. Okay? And so, this a represents the important feature about the system dynamics and the equation formation. Okay? So, we define new variable, tau value, which is equals to what? The 1 divided by a. Okay? And so, the a is greater, and then the time response, tr, is what? Huh? Decrease or increase? Increase. Which guy? Who says? Yes. If the a is increase, and then the time constant is decrease, but the time response is fast, right? And so the tau value is decrease. Okay? And so these are the parallel notation for the what? For this term. Okay? And so the time is decrease in here, and so the a is greater, and so the R system can be fastest as many as the what? The a permits this system, and so the tau value is decrease. Okay? And so these are the basic notation about the what? About the time constant. And so the time constant represents the what? The how our response behaves in the time. Okay? And so if we define these terms and then the R equation, is turned into the what? The 1 divided by tau x is equals to the b. Or we can write the tau x dot plus x b tau. Okay? These are the what? The first order representation of the time constant equation. Okay? This is important because if we want to model any system based on this property, and so this property preserved. But we can apply the different time constant values, or we can apply the different input values with the b. Okay? So if we have this equation, and then just remember that we have the xt is equals to what? The b divided by a plus x0 minus b divided by a times e over minus at. Okay? And so how we can write the time constant in here? Just see that time constant is equals to what? The 1 divided by a, Yağmur, right? And so how we can write this? B times tau, right? And plus x0 minus b times tau times e t divided by tau, right? These are the equation. And so if we increase the time constant, and then the our steady state value is what? Decrease or increase? If the tau decrease, and so steady state value increase or decrease? Just see the equation, guys. See, if the tau is decreasing, and then the steady state response what? Decreasing, right? And so if the tau is decreasing, and then the R transient response is fast or slow, which one? What's your name? Yes. Zina. R transient response is fast or slow? At the what? At the tau is small. Yes. Small or fast? If the tau decreases, and so the R system behaves faster than previous one, because we have the 1 divided by tau, and so the tau is decreasing, and so this distance is fastest, as many as possible, right? So here for x0 value, the xt is equals to what? The b times tau minus b times tau times e minus t divided by tau. Okay, these are the equation for this notation. Okay, and so we can write that the b tau 1 minus e minus t tau. Okay, these are the solution for the what? For beginning with the values of the what? What's your name? Ulaş. X0 is equals to the what? Constant, but the what? Initial conditions. This x0 is equals to the what? For this solution. No. So what is the values of the x0? No. Huh? What's the values of the x0 at this solution? Xt is equal to what? The b tau minus b tau e blah blah blah. What is the x0? Yes. 0. Arkadaşlar niye söylemiyorsunuz bunu? 0 işte yani hani. 0. See? These are the first equation, and so the x0 is 0, and so the R equation turns into the what? Into this one, right? Zina. Is that right? Zina, okay. So we can draw the figure, but which guy? can help me about that. For example, what's your name? What's your name? Süleyman. Okay, Süleyman. Please help me to draw this figure. And so we should assign the t, and we should assign the perpendicular, and so the xt can be assigned in here. And so if the t is growing right now, that how the r signal behaves like this. Just help me. Huh? Goes infinity or yes, but so what's your name? Mehmet. Okay, Mehmet. Just tell me. I should draw this time history, the time response on this graph. How should I do? For example, if the t is going to the what, the infinity value, what is the values of these terms? Huh? B tau? Yes, that's right. It's equals to the what? B times tau, right? See? And so these are the final condition for the, for the R signal, because if the t is going to infinity, and so this term is removed, and then we will have at the end of this signal this one, right? This region. And so how should I draw this line? What's the first point? 0. Why? Huh? Yes. That's right. And so this is our the first condition, the 0, right? Right? And so this signal is going to what? Just like this one, right? 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 Or wrong? Wrong. Why? 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 Why, Ajar? Huh? Yes. Yes, that's right. Thank you very much about that. So what's your name again? Sarah. Sarah. Okay. Thanks for the help, Sarah. I can correct my wrong. Oğlum telefonu bıraksana elinden. Sana diyorum. Süleyman. Hı. Tamam. Okay. And so this is right, Süleyman. This is right or wrong? Okay, thank you. So because at each case, if the t is going to what, the infinity value, and so the r value should approaching, just the Sarah said, the approaching to what, the b times tau value. Okay, and so in order to do that, we have the bigger difference value or differential derivative value at the beginning. But if we are closing to the what, the t is going to the infinite value, the change is going to what, the 0, right? And so it's going to what, just like this one. It's closing to some points in here. But in the first case, I draw the what, this signal. If this signal is going to just like that, and so this signal's what is going to the infinity value. Okay, this is why we should draw this signal. Okay, so and then we need to define some basic points in here. For example, e over minus 1. And so this is the 1, this is the 2, this is the 3, this is the 4. Okay, and so we have 2 points in here: e minus 1, e minus 2, e minus 3, e minus 4, right? Why this is equals to the e over minus 1? What is the values of a here? Huh? 1 over tau. But what is the values of it? If I choose to write the 1, 2, 3, 4, and so this curve must be changed with the what? With the time parameter, just like this one. T divided by tau is equals to the 1, 2, 3, 4, right? Because it's equal to the what? E over minus 1, E over minus 2, E over minus 3, E over minus 4, right? This is the standard representation of the what? The our time response based on the tau value, time constant value, okay? And so, if this is the case, we can formalize the general representation of the time response based on this information. And so we have two important points in here. First of all, at every first order equation, we have the 0.63 b dot tau value in here. For the what? For the 1. With respect to what? T divided by tau value. This is the R what? R basic parameters. To what? To standardize as a make it general formulation for the what? For this response. And so, if we have the t value and the tau value, if we draw these things, and so the 1 point is equals to what? 0.63 times b times tau value. Okay? This is always happen. This is always same for every system. If we can choose the t divided by tau at the x-axis, okay? At the y-axis, we have the xt value, and so this values is equals to the what? 0.98 times b tau value, okay? This is the standard formula to what? To derive the R basic parameters, okay? So, Süleyman, why we have the 0.63 times b times tau value at the what? At the 1. I don't know. So anyone knows that? Anyone guess that? If we divide the t with the what? With the tau value, our formulation is normalized based on the time, because the time constant is utilized to what? The normalization of the time parameter in the time response. And so, if we divide the t divided by tau value in here, and so we normalize the time response parameters based on the what? Based on this condition. For example, if we choose the tau is 2 or 5, and so this graph always same with the previous one. Okay? Because the tau is also changed. Tau is also changed. But the shape is the same. Which is why we need to use the what? The tau value in here. Okay? Şimdi arkadaşlar bakın. Buradaki sorun ne biliyor musun? Şimdi Türkçe açıklıyorum. Sen söyledin diye. Şimdi bakın. Bu grafik asla değişmiyor arkadaşlar. T bölü tau yaptınız ya. Zamana göre normalize ettiniz bunu. Anladınız mı? Zamana göre eğer normalize ettiyseniz bunu, sol taraftaki o xt değerleri de değişmiyor. Anladınız mı burayı? Yani ben hep birinci değerinde bunun t bölü tau Süleyman. Birinci değerinde hep 0.63 çarpı b çarpı tau değerini alacağım ben. Hep abi 4 değerinde burada 0.98 çarpı b çarpı tau değerini alacağım. Çünkü zamana göre normalize ettim ben bunu. Bu grafik hep aynı kalıyor. Birinci derece sistemler için. Burayı anladınız mı? Böyle bir ilişki var sistem dinamiğinde. This is why we need to use the time constant. Time constant is the general parameter, just like the mass or the speed of light. We can formalize everything and relate it with the time based on this parameter. We can normalize the time shape, the time parameter, based on this information. This is so useful to design the system dynamics. If we design it, and so we can control throughout the whole process, or the whole time response of our system that we designed. Zina, you understand that? Okay? Okay, you just repeat these things, okay? If you understand. Okay, I'm waiting.
For every system for first degree,
Uh-huh.
this kind of relation, it is something for all of the system, doesn't change.
Yes.
Every one we're gonna have 0.63, for every 4 we're gonna have 0.98.
Yes. Yes. Thank you. Thank you. And so this b dot tau value is equals to the what? The XSS, or the steady state value, guys. Okay? Which call it the steady state value. So we need to continue with the what? The transfer function. What is the transfer function, guys? Can anyone knows that? Can anyone say that? For example, what's your name? What's your name? Ah, Berkay. Berkay, what is transfer function? Okay. Okay. Yes. The input and the output. And so we can relate the input with the output, with the transfer function. Süleyman, what about these things? You don't know? Okay. Okay. And so I'm just here to teach you. The transfer function, Süleyman. Normally, we have the linear ordinary differential equation, right? Ordinary differential equation possessed what? The d divided by dt, d over dt parameter, or the derivative term, or the integral term, right? We have, for example, the x dot, and so. But we cannot easily do this ODE in the what? In the derivative terms. And so we need to convert these terms into the what, Süleyman? Into the algebraic one, which we should use to what? To Laplace domain, right? Okay. And so if we use the Laplace domain, and then we can define this ordinary differential equation into as the block diagram. Okay? And so we can put the what? The input, output, and so the R system at the middle of this input and output, right? So just remember that x dot plus ax is equals to the ft. And so if I take the Laplace transform of these terms, Süleyman, just tell me the Laplace transformation of this equation. Just try it. Try it. Don't be afraid. Dur oğlum, arkadaşın söylesin. Öğretmeye çalışıyoruz ama. Okay. The Süleyman doesn't know, but I'm here, and so we have the dot value in here, right? And so we need to put the what? Huh? S, right? S. And so the x0 considers the what? The zero value in here, and then this is the xs plus a times xs, and so we should equalize what? The fs, right? And so this is our equation, and then we can write it. Which one is the input? Which one is the output? And so, Hacer? Huh? S? No. S? No. S is the Laplace variable. Just write. Just tell me. Yes.
X the input,
XS is
input.
no.
Fs is input.
Yes. Thank you, Yağmur. Fs is the input, right? fs input, xs is the output. If we want to draw the time response of this value, and so the xs is the output, because we want to measure it, Mehmet, right? And so fs is the external one, and so if it's the external, and so we can call it the input, right? And so what is the values of this equation in here? Huh? 1 s plus a, right? Or 1 divided by a. Okay. And so this is also equal to the what? The 1 divided by s plus 1 over tau, right? And so this is the what? This is the frequency time constant, right? Or the frequency constant. This is the what? Time constant. And so the transfer function roots represents to the what? The frequency constant, and so, or inverse of time constant, right? Is that true or not? Is this true? So this is true because I wrote it. Okay, I'm always